Excited to be here. Good afternoon, all. My name is Aashraya. I'll be presenting LiveMLP, which is a machine learning platform for real-time use cases. So in the morning, we saw, right, there are multiple scenarios of SRE patterns. So we currently are following an ad hoc pattern. So it's mostly a journey of an ML engineer venturing into SRE world. So I'll try to go over what are the use cases we are solving and how are we able to roll it out to our customers in a reliable fashion. And along the way, I'll try to introduce some of the patterns that we have discovered, introduced to make the system more reliable and scalable as we roll out to 10,000 plus concurrent calls in a single session. So I'll just begin with a prologue in terms of what business use case we are trying to solve. So contact centers in general, the use cases can be bucketed into three distinct things. So first and foremost is quality assurance and operational efficiency, which is largely around, if you call a particular call center for, say, your food is delayed or something, your bank is not working, or your, anything related to third-party vendors. The first thing is how efficiently is the agent able to handle your queries, and we would like to monitor that in an automated fashion. Now, once we have established that there are certain gaps in ways the agents are not able to capture your needs, then how do we make sure that the performance is increasing via automated coaching workflows? And finally, this entire thing needs to happen in a compliant fashion. So based on where these workflows run, this entire thing can be broken down into either after interactions. So you would want most of these automations to run after the call has happened, or you would want these interactions to happen during the call. So for example, we would like the agent to have a safe way of answering any objections that a customer may throw at them, so on and so forth. Giving another example of bunch of use cases. So for example, we would like the agent to know, what are the sentiments found in the call, or what are the next things that they can say so as to answer you more appropriately, or refer to any knowledge base articles that may help them answer better as well. Now, to have a gist of this in terms like, what if any of this information is delayed on agent's portal, right? What if I had to say something, but because the ML couldn't predict in time, or the feature was not delivered to the front at the right time, that moment has passed away. So at that particular second, whatever you suggest, whatever you infer, whatever you predict is actually a distraction for the agent who's actually looking at the algorithm. So this entire system needs to be highly, highly latency sensitive. Needs to be very, very real time. And in fact, to the point where if there is a delay in the system, it's better to have loose messages instead of predicting behind the time. So with that context, I'll begin this talk with a quote of Leslie Lamport, who's actually one of the pioneers in distributed systems, which goes on to say that the failure of a computer can cause other nodes to fail in a system without you even knowing. And this is something that we do not want in the system that we are trying to build. So I'll try to design a system from grounds up so that some of the, is it gone? Okay. The screen went off for a while. Sure. Cool. Right, so we'll try to design a system so as to not cause any failures at scale as we are rolling out to other customers, so on and so forth. Okay, so what do we want to build? So this is an overall workflow or high-level diagram in terms of what do we want to build. So you have an agent who's usually interacting or taking calls or interactions via a console. The console is interlinked to a call center software via which they are able to interact with all the customers. The system itself further can be broken down into three subflows, where you have a call event listener, which actually listens to start and the end of the calls. Then you have an ASR system, which usually converts your the calls into text. And then this entire thing needs to be put down into an ML processor workflow, where different workflows need to run in parallel, in tandem, so as to generate certain triggers. So these triggers are generally what we call intelligence. And these triggers are then mapped to a particular actions that is then showed on an agent's dashboard. So this, going back to this particular example. So for example, here the trigger could be that negative customer was found in the conversation, what would you like to say next? So that's one of the actions, right? Somebody said my order number is this. So based on when the order number is detected, what kind of other workflows can you trigger in terms of, where is my order? How far is it running behind? So on and so forth. And all these ML processes are further backlinked into an inference platform where all the heavyweight ML models are running. Now, apart from this online system, there is an offline system that works in the background, which measures the model performance, which we saw in the last talk. Then based on the model performance, we also like to retrain model over time, which undergoes a model evaluation phase and then pumps back into newer versions of model into the inference platform. Now, for this particular talk, I would like to focus on the reliability and scalability of the trigger detection systems in terms of how does different ML processors, they work in tandem, how to design them from ground up for latencies. Okay, so what do we want to answer? To begin, I have bucketed the talk into 3 distinct sections: scalability, fault tolerance, and observability. And there are certain questions that I have put up front, which we would like to answer with the system that we are proposing. So for scalability, the first one is, what should the system look like if thousands of calls happens at once, right? So what if you have hundreds of thousands of agents in your system, and they start making calls or they start receiving calls at the same time? Would your ML backend scale with the load that it's able to take? What would it take to ensure that the consistent latencies are met at scale? So whatever latencies you get for one call, you should get it for 10, for the next 100, for the next 1,000 without deterioration. And what would be the limitation of such an infrastructure at scale? So is there a point where we can anticipate that the design that we are building, it is bound to fail, so as to we can anticipate when do we want to improve our systems going forward? The second bucket is fault tolerance. So what if a particular service crash, right? What if your intent detection service crashes? Does it mean all the services related to it needs to crash? Does it mean your entire system goes down? Or is there a better way to handle it? What if the entire instance which is hosting your one particular workflow or one particular call goes down? Are there ways where you can, repick that workflow from where it was? And what if there is a communication failure between infrastructure and service? How do you recoup from that? Then comes observability, where we track, what are the APM metrics do you need to monitor for such a workflow? How do you monitor pipeline level SLAs? And what are the infrastructure level KPIs that we should monitor as we roll out the system? So developing on these questions, I'll start with a train of thought. So as with any system design, before implementing, we should give it a fair bit of thought and try to justify some of the decisions that we are trying to make. So I'll try to convey my train of thought in a slow fashion, and we'll build on top of that. So the first thing is, what we can do is we can say, every voice that's coming into my system is a unique workflow per ML processing service. So if you have 10 different intelligence that are supposed to be processed for one call, then each of them are independent of each other and needs to run in parallel. So for every call, you'll have 10 workflows that needs to run. Every workflow is also stateful, because what you have said in the past in a call would matter the predictions that are supposed to happen in the future. So now you have 10 stateful workflows which are running. Each of them could be of any arbitrary length, because we do not know when the caller is going to end the call. And they can run for hours at a stretch. Then finally, workflow can only be assigned to a service if it's guaranteed a latency throughput. So I need to estimate ahead of time, if I assign a particular call to a particular service, would it be able to sustain the KPI of the latency throughout the call, right? If that doesn't happen, then I cannot do anything at scale. Then finally, once a service is assigned to a service, throughout the duration of that particular call, we would not want that particular call to be assigned to a different service. Why? Because first, the service is stateful. So any context switches would have an additional impact. And second, this switch would take more time to build the context again, and that would hamper your KPIs. Okay, now that being said, if it fails for some reason, that could be out of our hands, then it must be reattempted, because the call is currently still happening. The call has not ended, right? We should be able to track what workflows are mapped to what service processes, This is, again, a prerequisite for assigning workflows to services as well. But there should be an easy way for me to know, where is this particular call mapped to which ML process. There should be an easy deterministic way to scale services. This is, again, a requirement because we want high, very consistent KPIs. And obviously, there should be a way to monitor services and measure KPIs at each individual workflows. Okay, so although this is applicable to the current scenario that I have described, most of these core design philosophies actually applicable to any real-time ML system that you would want to run at scale. Right? Anything that has a near real-time latency and a throughput requirement, this is a must. Cool. So now, based on this particular thing, what we thought about was a Scheduler-Agent-Supervisor design pattern. So it's a known pattern, but we have slightly modified it for ML workflows. So what we do is we logically split our entire system into two distinct units, right? So on the thing that you see in the purple is what is called the entire brain of this distributed system, and the one on the green that you see is a cluster of agents. So in the purple system, what you see is a scheduler. A scheduler is the brain behind managing the task that needs to be run, right? So if I have 10 calls coming, if I have one call coming in, which is supposed to be mapped to 10 workflows, the scheduler will decide which of these workflows goes to which of the ML services. Then the scheduler is directly linked to a supervisor. A supervisor is supposed to manage how are the tasks that are currently assigned, are they progressing? Are there any delays in KPIs? Is any of them failing? Do I need to switch them to another server so as to give you better latencies? And they together interact with a common state store where state and the progress of all the KPIs being met, as well as the health of all the services being maintained. Now, the green cluster, which is the agent cluster. So every agent can be considered as a cluster of ML services, right? So if I have, say, entity detection or sentiment detection, then entity would be a cluster of its own where you'll have a pool of multiple ML models which are waiting for calls to come in. And then based on the state store, they would asynchronously pick few of these calls only when they can ensure that the KPI is being met. I'll quickly come to, how do you know where KPI is being met? How does the agent estimate that? I'll come to that part when I go over the scalability bits. Cool. So based on this pattern, what I'll do is, so we saw this diagram before. I'll expand on the green blurb on the extreme right. And what we end up is having this kind of low-level diagram which takes that particular SAS pattern into consideration. So now for call event, you have a call monitor that actually monitors when are the calls starting. Then all these things are then asynchronously pushed to a cache, which maintains one queue or one stream per ML processor. Each of these ML processors gets their own unique clusters. So for example, sentiment could be ML processor 1, summarization could be ML processor 2. Entity detection could be ML processor 3, right? And each of these clusters would have bunch of pooled resources which would asynchronously pick some of these workflows from their own queues. So all these queues are distinct from each other. And finally, you have a communication channel, which is a shared channel where you get transcript stream, and output of each of the ML processor is also put in the same stream, right? Now, why is that? So communication channel is supposed to be many-to-many because output of one ML model can be an input to another ML model. What do I mean by that? Say an entity service detects an entity, but a summarization would require that entity output to produce a summary of that particular entity, right? So now if you have, say, 50 of these services, the 50 of these services could have interdependencies amongst them where 49 outputs could impact output of the 50th service. So you need a scalable communication channel that does many-to-many mapping without failure. In addition, this also stores the transcript stream that's coming out of the ASR, which obviously is an input to all the services. And finally, the output which is required to be shown on, say, agent's screen can be read by an external service which you are calling trigger to action. And all the messages can be tagged based on type so that every services know which message to read when. Cool. Now coming a bit on the tech stack. So active call monitor, as I said, acts as a supervisor and a scheduler based on the SAS manager. So it knows what calls are coming in, how to populate them. So it's simply a Python microservice with a state maintained in Redis. Active call cache is currently also in Redis distributed mode, but it acts as a state management for active call monitor. It also maintains all the health check for all the workers, which in our case is ML services. It also maintains unique queues for all ML processors. Coming to ML processor, so this is where the workflow or the intelligence happens. So this is the agent or agent in the SAS pattern for processing the workflow. Currently, this can also be modeled as a Python microservice with an in-memory buffer. And this also has mechanisms to offload the model state, which is the ML model state, to a particular cache in terms of failures. I'll come to that design pattern as well. And then communication channel can be simply modeled as a Redis in distributed mode as well, which gives you many-to-many communications with redundancies. And we do maintain one stream per active call. So if you have 100 calls, you'll have 100 streams so that all the data, all the intelligence can be just read from a single stream of data. Right. Quickly going into a bit deeper into the inside ML processor. So the ML processor itself is split into consumer, producer, and a call worker. Call worker is the one where the intelligence of when to pick a call so that KPI is handled, that logic is stored. It also is supposed to send out health alerts on a regular basis of time. The consumer and producers are just supposed to consume messages on which intelligence is to be run. And then producer gives out output of the ML model in terms of intelligence. Finally, there is an in-memory buffer because all these things are stateful. So we maintain an in-memory buffer, which is then passed on to an ML inference process. ML inference process in general can be shared across multiple such workers because ML model in general is costly to host, and having resource time slicing across it makes more sense, from a cost perspective. So how do we manage, you may ask, how do we manage latency when we are optimizing for cost? So we will come to a pattern where how do we identify these numbers at scale? Like what is that number that lets you best cost for best accuracy? Cool. Now, once you have established this particular pattern, let's try to see how does this scale, like how do we do scalability, fault tolerance, and observability on top of these things? So let's start with scalability. The first one is obviously load balancing. So in any REST-based service or a lot of protocols where you have push-based things, it's really hard to maintain KPIs because you do not have a fine-grained control in terms of where is my request growing. If it ends up being on a resource that does not have capacity to do it at the latency we want, then it's of no use. So the first one is pull-based. So the call worker itself is intelligent enough to only accept a new workflow when it's able to sustain the latencies. The second one is the sidecar management. So any queue or any stream where you would like to have a pull-based services, they have limits in terms of connections. And once you are running multiple systems at scale, you are bound to run out of connections. So for example, Kafka, the Confluent Kafka itself have limits of say 5,000 connections. So if your every instance is running say 100 connections, you can only scale up to 50, which does not make sense when you have like 10,000 of them. So you need an intelligent way to reuse the connections that you have. So you need a software layer in between that does that connection management for you at scale, so that multiple different processes can have single redundant connection to the call cache that you are maintaining. And finally, the active call cache itself, you'll need to distribute load across multiple shards or replicas, whatever you want to call them. And you can make the sidecar intelligent enough to read only from the read replicas. And the write replica is only handled by active call monitor because it's the only one writing to it. And that ways you can further increase the number of connections that you can spawn from one instance or a single instance of such a cache. Right. The second thing, the similar thing also is applicable for communication channel, where you would need pull-based, not pull-based things, but sidecar patterns as well as read-write replicas, because it's again many-to-many connection pool layer which is shared across multiple ML processes. Right. Finally comes the ML processor. So as I mentioned, the ML inference itself, it needs to be batched. So there is a different way in which ML works as opposed to the other CPU-bound services, where the GPU itself has limit in terms of how much it can expand. So if you're running on a GPU of say 24 GB memory, and if your every inference takes say 16 GB on batch 1 and 20 GB on batch 2, that means you cannot ever run it beyond batch 2. You have to make sure at the client side, not at the server side. So this software layer in between makes sure that you get the best bang for your buck while batching, intelligently batching and memory-based load balancing. So based on the length of the buffer that you're having, it will intelligently load balance in terms of how many batch can I hit my model with. And that's how the ML processor is load balanced internally in general. Finally comes the auto scaling, which is, I think, should be very straightforward, where a lot of the APM matrix we gather from the ML processes, as well as the active call cache, they are fed into a rule-based system, which internally goes to a container orchestrator, which will scale your processes as and when required. So let's say to begin with, you can handle say 10 processes per instance, and suddenly you get 100 calls. So based on the statistics in the active call cache, you will automatically get 10 instances running, which would be ready to accept 100 connections at a time. Cool. So that solves for scalability. Coming to fault tolerance. So fault tolerance also, there are two things. One is the fault tolerance which can be caused by your own container orchestration. So in many of the container orchestrations, you would not have intelligent downscaling capacities. So it does not matter in REST, right? Because REST, you are having stateless services. Even if one instance goes down, it directly goes down to the another one. But here, if you are shutting down one instance, you have to make sure that there are no active calls running on that particular instance. If there are, then it's actually a loss. So how do we make that happen is we make our consumers or the ML processor itself intelligent enough to detect certain instances where it is about to be shut down. So Kubernetes, for example, would send you a sick term before killing the instance, and that actually is handled in the ML processor workflow so as to trigger a cleanup workflow. Which what it does is first it would unsubscribe from the cache so that no new calls is assigned during the period where it's being terminated. Then it would requeue the task that it was processing. So if I'm processing one particular call, I would store all its state back into the cache, and it will be available for the other instance to pick up. And then I would gracefully shut down on my own without the container orchestration to do anything about it. In terms where this particular flow does not happen, we do have a sick kill mechanism where, let's say, after a grace period of 20 minutes, if the instance doesn't go down, it is brutally killed by container orchestrations. That does have an impact on the KPI, but it's a needy behavior that is required. Now coming down to the cases where something is shut down inappropriately. So let's say something went wrong, or the sick kill was sent and the container did not shut down. So how do you make sure that the call gets reassigned again and starts processing again from where it left off? So again, the active call monitor here acts as a supervisor, and it triggers a supervisor workflow on regular intervals of time. And it monitors that what health matrix have not been coming up in regular period of time. It then identifies what calls were assigned to those instances, and it will automatically requeue certain tasks for which the instance heartbeat is missing or for which instance went down. Now, in this case, we do have certain deterioration in terms of you may lose certain inferences, but this is the speediest recovery that you can get from the last stored state that the process was at. Any questions so far? Cool. So coming to the final thing, observability. So we have solved for scalability and fault tolerance. How do we know what are the things that we want to observe for this particular scenario? So we have latency KPIs, stability KPIs, and infrastructure KPIs. So for latency, we would like to know what is the time to acknowledge a new call start notifications. So as long as some agent has started a call, how quickly can my system acknowledge it? That could be one KPI. Time to attach ML processor to a new call. Once a call has started, if it's broken down into 10 workflows, what is the latency of each of these workflows to pick up a new call that's coming into the system? Time to attach ML processes after a graceful and an ungraceful shutdown. So this is required for us to monitor how many messages or how many contexts am I missing in production as we are going ahead. And finally, time to process each transcript stream. This just tells me how quickly am I able to consume voice messages that are coming in, so as to know the real-time latency at which messages are being delivered to the end user. In terms of stability, we would like to know how many graceful shutdowns are we triggering. So do we need a better scheduling algorithm in Kubernetes, or the off-the-shelf is working for me? The number of ungraceful shutdowns, so as to check my hardware stability or any unwarranted bugs that I may have in the systems. And finally, number of network disconnections, which is the queues and the caches that I have. Am I dropping them? Am I dropping the network connections due to some network issues? And finally, infrastructure, we have the standard, the resource utilizations of the active call cache and the communication channel. We have the number of active connections, which is very important for any queue-based services. We have resources of all the ML processes as well as inferences. Then there is time to start a new container, which is very important when you are quickly scaling out from 10 to 1,000 calls. How quickly can you provision infra becomes very important. And then finally, cost per streaming, which is at any given point in time, what is the cost of the infra that you're hosting, and what is the number of voice calls that you're able to process with that infra. And this is what we do on observability. That leads to finally, how do we know whatever we have said so far is working in practice? So what we do is we have an in-house tool called Olaf, which is a distributed load generation and simulates voice calls. We take our entire system that we built in last couple of slides, and what we do is we start hitting it with thousands and thousands of calls. What we also do is we have all the metrics that I mentioned earlier already coded into the system, so that we already have an APM dashboard very similar to Grafana that was shown, which populates all these metrics as a function of number of calls that are running. And that gives us good confidence in terms of, are we missing something? Is there a blocker? And so on and so forth. Just to give you another pattern in terms of, many different ML models, they require different CPUs and memory. So how do you know which model requires what CPU and memory? So we use the similar system, and we iteratively double the load on a constant resource that we have. And then we measure the similar KPIs that we had initially. And we try to benchmark what is that breaking point of these infra where one particular ML model would break. Basically the resource of a particular service can vary on model to model. So a BERT model may require a GPU to run altogether, whereas an SVM-based model might just run on CPU. And finding this particular combination is very critical in terms of finding where the infra would break. What is that pull-based number that each consumer can accept, and also in terms of what is my cost to concurrent calls ratio. Great. So again, key takeaways in terms. So first and foremost, we need to understand for ML services particularly, do you want to optimize for throughput or latency? Both of them have different trade-offs. You can probably run on a smaller GPU if you want a higher throughput, but you will need a bigger GPU if you want a lower latency. Then how much lag latency can end system take? If your system is highly critical to latency, then it always makes sense to drop messages instead of pre-processing them, because first processing them would incur you cost and it would have no impact on the end user. And then finally, identifying the correct resources required for the model to keep up with KPI is another thing. In terms of communication channel, the first thing is how many services do we need to speak to each other? Is it one-to-one? Is it one-to-many? Is it many-to-one? What is that pattern? We need to identify whether the message can be processed on its own or do we need a buffer stream. So for example, any image-based task would be a singleton message processing system. You do not need additional uh, buffer to maintain them. But similarly for video, you may need to have stateful services that requires that. And then finally, identifying how long to keep the stream active for. So once the call has ended, do we want to store those predictions for post-processing or does it need to just go away? In terms of failure, should the stream be active so as to, you should be able to pick it up from where it left off, or you should start afresh? Observability is another P0 requirement that I think should be bundled with the system design philosophy itself. So you should be able to segregate KPI for services and platform. The services would entail what resources do you need, what GPUs, CPUs, but the platform would tell you what are the queue depth on which you want to scale, what are the communication latencies that you would need to minimize, so on and so forth. And finally, load test to avoid surprises in production so that when you go from 0 to 10,000, there aren't any issues. Great. That's all I had. Thank you.